Hey everybody. Before we go on to any more topics in computing derivatives or differentiation, it would be good for us to consider the topic of composite functions. And here's the definition of a composite function. Given the functions f of x and g of x, the function f evaluated at g of x is called a composite function. Now here's what we've done. We've taken the function f, and instead of plugging x into the function f, we've plugged an entire function g of x into the function f. And I'll talk more about that in a second. So this is f of g of x, or f evaluated at g of x, and we call that a composite function. As I've written down here, this expression, f of g of x, is called f of g of x, or it's called f evaluated at g of x. F evaluated at g of x. In other words, we're plugging the function g of x into the function f. The process of evaluating one function at another function, for example, f evaluated at g of x, is called function composition. Now, just look at that for a few seconds and let it sink in. And then I'm going to make some cautionary remarks. Let's make sure that we're clear on what this is not. This is not multiplication. This is not f times g of x. And it's not f of x times g of x. Just to make a distinction between the two, f of x times g of x looks like this. This is what f of x times g of x looks like. See, we have the f of x here, we have the g of x here, and each one, f and g, have their own variable plugged in. This is what f of x times g of x looks like. This is not multiplication. So this is the function f evaluated at g of x. F evaluated at g of x. And to get f evaluated at g of x, we take the function f right here, and we plug g of x into the function f. We take the function f, and we take g of x, an entire function, and we plug it into f the way we would normally plug an x into the function f. So this is not multiplication. This is function composition. We are taking one function, f of x, and we are plugging into it another function, g of x. Now, let's do some exercises. Okay, we're given two functions. F of x equals 3x squared plus 2x plus 1, and g of x equals 1 over 3x minus 1. Okay, f evaluated at 0. What is it? Well, most of us would probably say that it's equal to 1. Now I ask, how did we get it? And we say, well, I just looked up here at f of x and plugged in 0 for x, which is exactly how we get it. Now, why do we do that? This is our definition of f of x, our model, so to speak. This is f evaluated at x. That's our model, our definition. Down here we have f evaluated at 0. So 0 plays the role down here that x plays up here in our model. So every place up here in our model that we see in x, we're going to put a 0 down here. So we get 3 times 0 squared plus 2 times 0 plus 1, and we get 1. Now what about f evaluated at 1? If we think about it for a second, we're probably going to say that's 6. And then we're asked, how did we get it? And we say, well, I looked up here, and every place I saw an x up here, I plugged in a 1, which is exactly what we should do. But why do we do that? Well, here's our model, our definition of f of x. This is f evaluated at x. Down here we have f evaluated at 1, which means that down here, 1 plays the role that x plays up here in our model. So every place up here in our model that we see in x, we're going to put 1 down here. So we have 3 times 1 squared plus 2 times 1 plus 1 is equal to 6. And it turns out that we were right. Let's do another one. Yeah, I use this example every now and then. F evaluated at a ham sandwich. Yeah. How do we compute that? Well, think of what we have. Down here, a ham sandwich is playing the role that x plays up here. Because down here, this is f evaluated at a ham sandwich. So the ham sandwich plays the role down here that x plays up here in our model, f evaluated at x. So every place up here in our model that we see in x, we put a ham sandwich down here. And we're going to get 3 ham sandwiches squared plus 2 ham sandwiches plus 1. And if that's what we were thinking we should do, then we were absolutely right. Now, let me do this. F evaluated at g of x. Oh, and you know what? Son of a gun. I just forgot what g of x was. You know, I'm getting up there in age, and my memory comes and goes. I just forgot what g of x was. So I guess I'm going to have to give this answer in terms of g of x. This is f evaluated at g of x, which means that down here, g of x plays the role that x plays up here in our model, f of x. Because in our model, this is f evaluated at x. Down here we have f evaluated at g of x. G of x plays the role down here that x plays up here in our model. So every place up here in our model that I see an x, I'm going to put a g of x down here. So I have 3g of x squared plus 2g of x plus 1. That's what f evaluated at g of x is. And you know what? I just remembered what g of x was. It's 1 over 3x minus 1. Okay, so in the next step, I can just plug in the equivalent expression for g of x in terms of x. 3, 1 over 3x minus 1 squared plus 2, 1 over 3x minus 1 plus 1. Ah, very, very, very good. Now for my next example, I want f evaluated at f of x. Now that seems strange. I bet a lot of us didn't know we could do that. Evaluate a function at itself. Yikes. Well, I intend to do this exercise exactly the way I did the one above it. I'll write it out in terms of f of x, and then I'll go from there. And what I have down here is f evaluated at f of x. Up here I have f evaluated at x. So f of x plays the role down here that x plays up here in our model, which means that every place up here in our model that I see an x, I'm going to put an f of x down here. So I'm going to have 3 f of x squared plus 2 f of x plus 1. And now I can substitute 3x squared plus 2x plus 1 for f of x. Ah, voila. Now look at that for a second or two, and we're going to do some new exercises. G evaluated at 0, what is it? We probably look at g of x and then say, oh, it's -1. And we're asked, well, how did we get that? We say, well, we took 0 and we plugged it in here for x, which is exactly what we should do. Now, why do we do that? Well, here's the definition of g of x. This is g evaluated at x. So this is our model of g, the function. Down here we have g evaluated at 0, which means that 0 plays the role here that x plays up here in our model. So every place up here in our model that we see an x, we're going to put a 0 down here. Okay, let's try another one. G evaluated at 1. 1 plays the role here that x plays in our model up here. So every place that we see an x in our model up here, you guessed it, we're going to put a 1 down here. So what is that, 1/2? Okay. And drum roll, please. Drum roll, please. We're about to welcome back for the second night in a row our special guest, Mr. Ham Sandwich. We have G evaluated at a ham sandwich. Yeah, it may seem silly, but we can do this. Down here, the ham sandwich plays the role that x plays up here in our model. So every place that we see an x up here in our model, you guessed it, we're going to put a ham sandwich down here. So we get 1 over 3 ham sandwiches minus 1. Beautiful. Beautiful. And now that we've done that, let's do this. G evaluated at f of x. Oh, and you know what? I just forgot what f of x was. Yeah, the memory, it comes and goes, you know? So I guess I'm going to have to express my answer here in terms of f of x. This is g evaluated at f of x. So f of x is playing the role down here that x plays up here in our model of g. So every place that we see an x up here in our model, we're going to put an f of x down here, aren't we? So we're going to get 1 over 3 f of x minus 1. Excellent. And I just remembered what f of x was. Son of a gun. It's 3x squared plus 2x plus 1. So now I can finish this. It's going to be 1 over 3 times f of x, but that's 3x squared plus 2x plus 1 minus 1. Cool. And never one to waste a good exercise or quit while we got the ball rolling. We're going to do one more. We're going to do g evaluated at g of x. And we're going to do this exercise exactly the way we did g evaluated at f of x. We're going to write it out in terms of g of x first, and then express it in terms of x after that. Here we have the function g evaluated at g of x. So g of x plays the role down here that x plays up here in our model. So every place we see an x up here in our model, here and here, we're going to put g of x down here. So we're going to have 1 over 3 g of x minus 1. And now we can plug in 1 over 3x minus 1 for g of x here. Bravo. That we need to get a handle on, what do we call these? Composite functions, yeah. Because in calculus, not only do we compute the derivatives of products and quotients, but more often than that, we compute the derivatives of composite functions. So before we can compute the derivatives of these monsters, we need to get a good handle on exactly what a composite function is. We don't really have any homework exercises in our text along these lines, but I do have some on my website, and I will be assigning those exercises right along with this video. And don't underestimate the importance of composite functions. If we learn to do calculus with composite functions and we learn to do it well, that will not only help us with Cal 1, but it will make a world of difference for us if we're taking Cal 2. It's a make or a break for Cal 2. to get down the calculus of composite functions. So let's study this video and let's do the homework exercises in earnest, because maybe just like me, when I made the transformation from being a poor student to a good student, maybe we're a good student already. Or maybe we're in the transition from being a not so good student. We want to be a good student now. This is how we do it. We do the homework, we do the studying, we do it in earnest, and son of a gun, we'll understand mathematics like we never understood it before. As a matter of fact, this method works so well that even I understand it. So it's got to be good.